So today our discussion will be on enthalpies for different types of reactions. The first one is standard enthalpy of combustion, denoted by this symbol delta CH minus. So it is the enthalpy change, per mole or per unit amount of a substance when it undergoes combustion, and all the reactants and products being in their standard state at specific temperature. So the reactants and products should be in their standard states. Now let's see one example, to understand it better. C4H10 gas, with oxygen to give carbon dioxide and water molecule. So this one is butane, and it is mostly found in cooking gas, in cylinders. So in combustion, what happens? This is heated, in presence of this one oxygen. So in combustion, what will happen is bigger compound will break into smaller component. So 13 by 2 and 5. So the combustion or enthalpy of combustion for this one will be minus 2658 kilojoule per mole. So in this case the reaction is exothermic. Heat is released. Now let's see another example. C6H12O6 plus oxygen to give carbon dioxide and water molecule. In this case, what is happening is combustion of glucose is taking place in presence of oxygen. So usually this takes place. This is an example in our body. So our body generates this enthalpy also. That means heat. But there are other kind of processes involved also in this case, like biochemical reactions involving enzymes. So to get this final product, other processes are involved, like the biochemical reaction involving enzymes. Now let's see the next one, enthalpy of atomization. In this case, atom will form. So enthalpy change, involving breaking of 1 mole of bonds. 1 mole of bonds to obtain atoms in the gas phase. So this is a change, when 1 mole of bond is break to get atoms, in gaseous phase. Now one of the simplest example will be this one, Na solid, Na gas. So it is turned into gas, for this case. So this is same with the enthalpy of sublimation. So this solid change into vapor. So this is known as sublimation. Another example is methane, which is a gas. Gives carbon plus 4 hydrogen. Okay, so this 1 mole is okay broken down okay to this carbon and hydrogen. Okay, that means carbon atom and hydrogen atom. Okay, so the energy involved is the enthalpy of atomization. So in this case heat is absorbed. Okay, that's why we are writing 108. Okay, plus. Okay, that means there is no negative. That means it is endothermic process. Let's see the next one. Bond enthalpy, okay, denoted by this delta bond H minus. So we know that in chemical reactions, okay, what will happen is bond, let's say AB, okay, or CD, okay. In chemical reaction, what will happen is this bond will break, okay. This will break into individual ion, okay. Let's say A plus B minus, something like this, okay, or A plus B to give A B. So in chemical reaction bond will break or bond formation will take place. Okay, so when this bond is break, okay, energy is required. Okay, we need to add energy. Okay, add energy. Okay, so when bond is formed, energy is released. So energy will be released during the formation of bond. This will be exo and this will be endo. Okay, so when bond breaks, okay, endo, that means heat should be supplied, okay, to initiate this bond breaking process. And then when bond is formed, heat is released. Okay, when AB combined, heat is released, something like that. Okay, now enthalpy changes, okay, can be associated with these chemical bonds. Okay, so in this case in thermodynamics, okay, these changes can be of two types. Okay, one is bond dissociation enthalpy and the other is mean bond enthalpy. So what is bond dissociation enthalpy? Dissociation means breaking. Okay, so in this case bond breaking will take place. Okay, so let's see. It is the enthalpy change when 1 mole of covalent bond of gaseous covalent compound is broken to form products in the gas phase. Okay, so in this case what will happen is 1 mole of covalent bonds, okay, so like this, okay, it will break, okay, to form products in the gas phase. Okay, so this will be when the product is formed, it will be in gas phase. Okay, gas phase. Let's see example. So usually the diatomic molecules, they will show this bond dissociation enthalpy. Okay, the simplest example is the hydrogen gas, okay, breaks into hydrogen, this, okay, so bond dissociation enthalpy of this will be 435 Kelvin. Okay, kilojoule per mole, sorry, not Kelvin. So this covalent, okay, in this hydrogen we will see covalent bond, okay, and this, in order to break this bond, this much of energy is required, that means, okay, so it is known as bond dissociation enthalpy. Okay, so another example, let's see one example. Chlorine, okay, gas to give Cl, okay, chloride. okay. So the bond dissociation enthalpy here is 242 kilojoule per mole, okay. So like we have discussed earlier, okay, when bond breaks, heat is absorbed, that means endo, okay. So these are in positive sign, okay. Now next one, polyatomic molecules. For polyatomic molecules, this bond dissociation enthalpy will be different, okay, for different bonds with the same molecule. That same molecule, okay, but each bond will have different bond dissociation enthalpy, okay. Example, taking example of CH4, okay, that is methane, okay. So in this case, methane breaks into C, and that means carbon and hydrogen, okay. So the overall bond dissociation, okay, or atomization, okay, this A means atomization is 1665 kilojoule per mole, okay. So in methane, okay, CH4, this CH, okay, bond are identical, okay, in length, okay. The length is identical, and even the energies are identical, but they show different bond dissociation of enthalpies, okay. Let's see those example here. The first one, CH4, okay. In CH4 it loses one hydrogen, okay, and becomes CH3, okay. The bond dissociation enthalpy is given here, 427 kilojoule per mole, okay. Now for CH3, it loses one, okay, hydrogen, becomes CH2. Bond dissociation enthalpy will be 439 kilojoule per mole, okay. Now for CH2, breaks into this CH and H. Bond dissociation enthalpy is 452 kilojoule per mole. Now CH breaks into carbon and hydrogen, so bond dissociation enthalpy will be 347 kilojoule per mole. So in this case, this one, okay, is showing the highest bond dissociation enthalpy, okay. In this case, what happened is, since one hydrogen is removed, this carbon will have 1 ampere electron, okay. So in this case also it becomes CH2, so it will have 2 ampere electron, okay. So as a result, okay, this show higher bond dissociation enthalpy than this one, okay. This CH2, okay, this will be 1 electron, okay, this will be 2 electron, 2 ampere electron, okay. So in this case, highest, okay, bond dissociation enthalpy, okay. And then for this one, 3 ampere electron, and since 300 electron are there, there will be repulsion, okay. So it shows less bond dissociation enthalpy than this one, CH2, okay. So this is the highest, okay, followed by this one, and this one. Now let's come here, okay, the second point, okay. What is mean by this mean bond dissociation enthalpy, or mean bond enthalpy? So this mean bond enthalpy means the total of all this, okay, divided by 4. So since 4 steps is involved, so we write 4, okay. So what we get is 416 kilojoule per mole. So this will be the mean dissociation enthalpy, okay. So if you remember this Hess law of constant heat summation, okay, so all these steps will be equal to this one only, okay. All these steps, okay, if you calculate, it will give you this one, okay. Now the standard enthalpy of reaction, okay, this delta RH, okay, related to bond enthalpies of reactants and products, okay, in gas phase. Okay, so please remember this bond dissociation, it will be taking place in the gaseous phase, okay, gaseous phase, not solid or liquid, okay, so gas phase, okay, please remember that. Gas phase, okay, is given by this one, delta RH, summation bond enthalpies. So in this case it will be reactant, okay, minus bond enthalpies, okay, product. So this is for the case of bond dissociation, okay. In the previous videos we have discussed about the enthalpy, okay. So in that previous video it was the product was here, okay, and reactant was here. Now we are talking about dissociation, okay. So for bond dissociation, reactant comes first and product is, okay. Next one is enthalpy of solution, okay. Symbol is del SOL H minus. So enthalpy of solution of a substance is the enthalpy change when 1 mole of it is dissolved in specified amount of solvent, okay. So when we dissolve 1 mole of any substance, okay, in a solvent, okay, the enthalpy, okay, change, okay, will be the enthalpy of the solution, okay. So one example, okay, is given from in your textbook also. So this AB solid, okay, dissolve, okay. So when it dissolve, it gives ion, okay, A plus and B minus, okay. So this aqueous means in water, okay. So we usually use this aqueous when we are using water, okay. So another step will be this lattice, okay, enthalpy or lattice energy, okay, breaks into this A plus gas, B plus gas, okay. So this lattice energy means when 1 mole of a substance, okay, breaks into these gaseous ions, okay, and energy involved here will be the lattice energy, okay. So when 1 mole of this breaks, okay, the energy involved will be the lattice energy, okay. So another one is, okay, this is the first one, okay. So this hydration enthalpy, okay. So this gaseous ions, okay, or these ions, or this mole, okay, let's say 1 mole of ions, okay, will undergo hydration, okay, in that solvent, let's say water, okay. So the energy involved, okay, when these ions are hydrated is called the hydration enthalpy, okay. So that's why we wrote A plus aqueous, B minus aqueous, okay. So usually okay, enthalpy of solution will be given by this lattice enthalpy and hydration enthalpy, okay. Let's, for better understanding, let's take Na plus Cl minus, okay. Suppose this is solid, okay. So this solid breaks into Na plus aqueous, okay, plus Cl minus aqueous, okay. So the step involve lattice A plus gas, Na plus gas, B minus gas. Okay. So in this case, what is happening is this in hydrogen. Okay, for lattice we know it breaks into these gaseous ions. Okay, Na plus and Cl minus ions. Okay, let's take it as gas. Okay, now in hydrogen, okay, this hydrogen, it will take place in solvent. Okay, let's say H2O, water, okay, as solvent. So in H2O, structure will look like this. Okay, so we know that this oxygen is slightly positive and this one hydrogen is slightly, sorry, this is slightly negative, this is slightly positive. Okay, so we know this Na will break into Na plus and Cl minus ions. Okay, so this Na will be, okay, attached. Okay, they will form bonds. Okay, in this case there will be interaction between Na and OH and Cl and H. Okay, so the energy, okay, involved, or the enthalpy involved when these ions are hydrated. Okay, when these ions are hydrated. Okay, hydrated means water is added. Okay, so energy involved in this is the hydrogen enthalpy. Okay, so this OH, they will come, okay, and interact with this Na. Okay, and Cl ion, okay, with hydrogen. Okay, like this. Okay, now from that Hess law of constant heat summation, this sum of this one, okay, these steps for 1 and 2, that is enthalpy, and this one, it will be equal to this hydration, not hydration but enthalpy of solution. Okay, next one, lattice enthalpy. Okay, so what is lattice enthalpy? We discuss here in a more detailed way. Okay, so lattice enthalpy. So the lattice enthalpy of an ionic compound is the enthalpy change. Okay, enthalpy change. Please avoid those background noise. Enthalpy change, which occur when 1 mole of an ionic compound dissociates into its ion. Okay, see, 1 mole of ionic compound dissociates into its ion in gaseous state. Okay, so this one dissociates into Na plus and Cl minus. Okay, so this will be in gaseous form. Okay, so lattice energy here is plus 788 kilojoule per mole. Now in actual case, okay, it is impossible to determine this lattice enthalpy, okay, by experiment. Okay, so this Born and Halber, okay, they developed this Born-Halber cycle, okay, to calculate lattice enthalpy, okay, through successive steps. Okay, different steps, okay, were involved. Okay, so let's calculate this lattice enthalpy of NaCl. Okay, so for this we'll see some steps. Okay, Na solid, okay, it's converted to Na gas. Okay, so enthalpy involved here is, this is known as sublimation enthalpy. Okay, solid sublime to vapor. Okay, so 108.4 kilojoule per mole. Now Na, this Na lose 1 electron. Okay, so this is known as ionization. Okay, or ionization enthalpy also. of ionization enthalpy, and write in short form here, is 496 kJ per mole. Now chlorine will accept this, sorry, in the next step, so half chlorine, okay, will form this Cl, okay, gas. That means this chlorine dissociates into this one, okay. So the bond dissociation will be this one, okay, 121 kJ per mole. Now this Na donates 1 electron, so this electron, okay, we know sodium, they are electropositive, so they donate this electron, and chlorine takes this electron, okay, Cl plus electron, and it becomes Cl minus, okay. So electron gain, okay. So this is now known as electron gain enthalpy. So electron gain enthalpy, in this case the process is exothermic, that's why minus signs come here, okay. 348 minus 348.6 kJ per mole. Now we don't know this lattice enthalpy, okay. Na plus Cl minus Na plus solid, okay. So in actual case the reaction will look like this: Na plus half Cl to give NaCl, okay. Okay, Na plus half Cl2. This will be 2, okay. I forgot to write this one. Half Cl2, okay. So let's see the Born-Haber cycle, okay. So this Born-Haber cycle is given, okay, here. So in the first case we did a sublimation, okay. So this Born-Haber cycle includes these 4 steps, okay. So sublimation, and then ionization, okay. Na lost 1 electron, okay. Bond dissociation, okay. That means this one Cl, okay, dissociate into chlorine, dissociate into this one Cl, okay. And then electron gain, okay, this chlorine, it gains electron, okay. So 1 2 3 4, okay, 4 step, 1 2 3 4 step, okay. So this one is formation, okay, enthalpy of formation, okay. So Na plus half Cl2, okay, combine to form this NaCl, okay. So the energy involved here will be minus 411.2 kJ per mole, okay. So when these two combine, okay, when bond is formed, we know that heat is evolved, okay. When bond breaks, heat is absorbed, okay. So this one, it's minus, okay. Now so this Born-Haber cycle, okay, this Born and Haber, they use Hess law of constant heat summation, okay. They use the idea of Hess law of constant heat summation, okay, to bring this cycle, okay, and to calculate this lattice enthalpy, okay. So how do we find this lattice enthalpy? We bring all the steps together and, okay, sum up all this, okay, and then we will get this one, this value 788 kJ, okay. So this will be the lattice enthalpy, okay, of sodium chloride, okay. 1 mole of sodium chloride, okay. When this 1 mole of sodium chloride dissociates into Na plus, okay, gaseous ion Cl minus gaseous ion, okay. So this is the Born-Haber cycle. Let's see the last topic, enthalpy of dilution. So this enthalpy of dilution is similar with enthalpy of solution. Okay, let's see. It is the heat withdrawn from the surroundings when additional solvent is added. Okay, so when we add solvent, but more solvent, okay, when we added, so please avoid this noise, okay, background noises. So when we add solvent, okay, the heat involved or the enthalpy change will be the enthalpy of dilution. Okay, so this dilution means we add more solvent, okay, to any acid. Okay, dilution means we add more acid. Okay, so if we adding more solvent to this acid, it will lose its acidic strength also. Okay, in that way. But here we are going to check the energy. Okay, enthalpy change. So this enthalpy of dilution will depend on the original concentration, okay, of the solution and the amount of solvent added. Okay, so the original concentration and the amount of solvent added, okay, will depend on that. Okay, this enthalpy of dilution. For better understanding, let's see this example. The first example is this HCl gas. Okay, in HCl gas is added with 10 aqueous. That means aqueous means water. Okay, so HCl 10 aqueous to give HCl 10 aqueous. So enthalpy involved here is minus 69.01 kilojoule per mole. Okay, so we use this symbol for our convenience. Okay, now let's see another one, S1. Okay, let's take this one as S1 or step 1. Okay, HCl gas plus 25 aqua, that means 25. Okay, HCl 25 aqua to give. So enthalpy involved here is 72 minus 72.03 kilojoule per mole. Next one, 40, so it gives 72.79 kilojoule per mole. Okay, the third mole. Okay, this omega symbol means infinite. Okay, after adding so much, okay, of that solvent, okay, we'll get this HCl. It's infinite dilution because it is infinite dilution also. Okay, so it will give delta H as minus 74.85 kilojoule per mole. So when we add more solvent, okay, it will reach a limiting value. Okay, so this is the limiting value. Okay, so at infinite dilution, okay, so in this limiting value, okay, it will reach to this value. Okay, this will be the limit. Okay, after this, beyond this, there is nothing. Okay, so it will reach up to this value. Okay, so this will be the limiting value. Okay, and from here also we can calculate the enthalpy of dilution. Okay, so we can subtract this S1 from S2. Okay, S2 and S1. Okay, so in this S1, if we add 15, we'll get 40. So HCl 25 aqua plus 15 aqua, 40. Okay, so subtracting these two, what we get is 0 minus 0.76 kilojoule per mole. Okay, so this is the enthalpy of dilution. Okay.